Now, and the second component is related to the amount of threshold voltage. That means the component of the threshold voltage that is needed to cause the surface conversion by twice the electrostatic Fermi potential of the substrate. Third one is the component related required to counteract or make the depletion region charge. Okay, and the fourth one accounts for the positive sodium ions that is present at the interface of the oxide and the uh, silicon substrate. Okay, so these are the four components. Note that this is a general expression that can relate to both NMOS and PMOS transistors. Okay, and also we see that in general, source and substrate may not be at the same potential. So when there is a relative potential difference between the source and the substrate, so we need to take care of that. Okay, so if VSB for NMOS transistor, VSB is normally greater than 0. Okay, so in that case, we have to account for the fact that it can lead to an increase in the depletion area charge. Okay, so then QB can be the depletion area charge for VSB greater than 0 and QB0 for BT0. For BT0, that means the zero bias threshold voltage. So QB0 corresponds to VSB equal to 0 and QB for VSB greater than 0 for NMOS transistor. Okay, then this body bias coefficient comes into being, where body bias coefficient is related to the technology parameters Na. Na is the acceptor concentration, then dielectric constant, electronic charge, and gate capacitance per unit area. This is a very important expression that we will have plenty of occasions to use. That means the generalized expression for threshold voltage is equal to the zero bias threshold voltage plus gamma, okay, root over this expression. Note that here why we write minus 2 phi f. So this will you know that phi fp is negative for p-type semiconductor and positive for n-type semiconductor. Okay, so for NMOS transistor, for example, phi fp is negative. So if you write minus, it becomes positive, and VSB is positive. But for PMOS transistor, VSB is negative. Okay, whereas phi fp is negative. So that's what. This expression can be used both for N-channel and P-channel MOS transistor. Okay, gamma, for example, is positive for NMOS transistor but negative for PMOS transistor. And here also I have written that specifically is some of the sorry, some of the terms and coefficients have different polarities, positive and negative for N-channel and P-channel transistors. Specifically, substrate Fermi potential 5 is negative for NMOS transistor. Why? Because the P-type substrate is there, and it is positive for PMOS transistor. In PMOS transistor, we have got the N-type channel or N-type semiconductor substrate, for which the 5N is positive. Okay, and here you have got the depletion region charge density. For NMOS transistor, the immobile acceptor ions are negative, whereas for PMOS transistor, the immobile donor ions are positive. Okay, for NMOS transistor, the immobile acceptor ions are negative, and for PMOS transistor, the immobile donor ions are positive. And substrate bias coefficient gamma is positive in NMOS, negative in PMOS. Then substrate bias voltage VSB is positive in NMOS, negative in PMOS. Typically, threshold voltage of the enhancement type NMOS transistor is positive, while that for P-channel transistor is negative. Let us see one example how to calculate the threshold voltage. Okay, VT0, that means the zero bias threshold voltage for a polysilicon gate. Okay, N-channel MOS transistor. Note that although we call it MOS, metal oxide semiconductor, nowadays in general the gate is made of polysilicon. Okay, this will aid the fabrication process with the following parameters. Acceptor concentration is 10 to the power 16 per cubic centimeter. Okay, donor concentration is 2 to the power 10 to the power 20. Now, 10 to the power 20 is orders of magnitude higher than the acceptor, 4 orders of magnitude. And the this is the thickness of the oxide dielectric, that is 500 angstrom. 1 angstrom equal to 10 to the power minus 10 meter or 10 to the power minus 8 centimeter. So this you need to be aware of. Then this is the positive sodium ions concentration, NOx. Okay, and it is in present in the oxide interface. That's why it is called to be NOx, subscript OX, that is 4 into 10 to the power 10 per centimeter square. And dielectric constant of silicon is 11.7. Dielectric constant of silicon dioxide is 3.97, roughly 4. And this is the free space permittivity, epsilon 0, we write it 8.85 into 10 to the power minus 14 farad per centimeter. Okay. And how to calculate? Remember that there are 4 components for the threshold voltage. Okay. So first component, first component is related to the difference of work function. Okay. So for that, you recall that for the substrate, which is p-type semiconductor, it can be written as kT by q into log of n by Na. And normally kT by q, the value is 26 millivolt at room temperature, and we take T to be 300 degree Kelvin. I believe it is clear, right? And log of Ni by A, Ni is the intrinsic silicon concentration, that is 1.45 into 10 to the power 10. And Na is 10 to the power 16, so this is minus 0.35 volt. As doping density of polygate is 2 to the power 10, 2 into 10 to the power 20 centimeter, that is very large in magnitude. Okay, so overall, we shall assume, this is mere assumption, the energy band diagram of NMOS polysilicon gate, if we draw for N-type degenerate semiconductor, EF almost coincides with EC. That means on the polysilicon gate side, as the concentration of the donor is much higher, 2 to the power 2 into 10 to the power 20. Okay, much higher than the other comparable density, like Na for the p-type semiconductor is only 10 to the power 16. This is 10 to the power 20. So for practical purpose, we can take that this is a degenerate as an example of degenerate semiconductor. And hence, tacitly, we assume that EF is almost coinciding with AC. This we can assume. Okay. So energy band diagram is shown roughly. Then EF almost coincides with EC. As the Fermi level of N-type poly gate is at the same level. Okay, so as far as the Fermi level of the N-type poly gate is concerned, EF and EC is almost coinciding. So that means the phi f is the difference of EF and EI. And for silicon, it is half of 1.1 electron volt. That means 0.55 electron volt. Okay. So work function difference between gate and channel is, we write as phi GC. That means it is the difference of the electrostatic Fermi potential of the substrate and that of the gate. For the substrate, we have calculated it to be minus 0.35, minus 0.35, minus 0.55, so minus 0.9. Okay, and next, then second component is minus 25 FP. Okay, that is minus 2 into 0.55. Acha. No, sorry, minus 2 into 0.35. That is the minus 25. Third component, if you have to know, that is equal to minus QBO by COX. Now, what is the, here we are supposed to calculate the zero bias threshold voltage. So what is the zero bias depletion area charge? That we can write in this form. Okay, minus root over 2 into Q. So if you put in the parameters, 1.6 into 10 to the power 19, Na equal to 10 to the power 16, this is 11.7 into 8.5, 8.5 into 10 to the power minus 14. Then 2 into 5, that means 2 into 0.35. All these parameters, if you put in the value, numerical value, you get it to be minus 4.82 into 10 to the power minus 8 coulomb per centimeter square. And oxide interface charge is this, Qx equal to Q into NOx. Okay, that means that is equal to 6.4 into 10 to the power minus 9 coulomb per centimeter square. Now, gate oxide capacitance per unit area, this is epsilon OX by TX. So we get it to be roughly 7 into 10 to the power minus 8 farad per centimeter square. Now combine the 4 components of the threshold voltage. So we can find out to be Vt equal to phi Gc, that is equal to minus 0.9. Why the minus 0.9 is coming? You see from this expression. That means here phi f substrate minus phi f gate. Phi f substrate we have calculated to be minus 0.35, minus 0.35, minus 0.55. So it is becoming minus 0.9. And then we have got minus 2 phi f. Okay, so there is minus 2 into minus 0.35. It becomes 0.7. And then QBO by COX. Again, you have seen the negative sign. So you get it, calculate it like this. you have calculated COX to be 7 into 10 to the power minus 8 farad per centimeter square. And finally, the fourth component, that means the QOX by COX. This is the component of threshold voltage required to offset or balance the positive sodium ions at the oxide silicon interface, right? So you calculate all the components, then find out the zero bias threshold voltage to be 0.4 volt. Clear? Now, frequently need arises to adjust the threshold voltage. Okay, that means let us address that point. Adjusting the threshold voltage by selective ion implantation. For N-channel metal oxide semiconductor transistor, threshold voltage is increased. That means it can be made more positive by adding additional p-type impurities or trivalent acceptor ions. Reason is that one needs to, what is the reason? That means if you make present acceptor impurities in the channel, it will lead to increase of the threshold voltage, or the threshold voltage will be more positive. What is the reason? Reason is that to offset or compensate for negatively charged acceptor ions in the channel, the top plate or gate must provide positive charge. That means the threshold voltage has to be more positive. Okay. On the other hand, if the threshold voltage of threshold voltage of N-channel MOS transistor can be decreased or made more negative by implanting N-type impurity. So if you have to reduce the magnitude of the threshold voltage, be it NMOS or PMOS, whatever, it is required to implant the channel region with N-type impurities or pentavalent or donor ions like phosphorus into the channel region. Achha, amount of change in the threshold voltage as a result of extra implants can be approximated as follows. Let the density of implanted impurities be Ni ions per centimeter square. Assume all implanted ions contribute to depletion region charge. This is also another tacit assumption. Then BTO for VSB equal to 0 is shifted by an amount QNI by COX. That means if the implantation takes place, ion implantation process takes place, and the density of implanted impurities is Ni ions per unit area, then we can calculate how much change in the threshold voltage it will result. That is equal to QNI by COX. Okay, charge by capacitance that gives you voltage. This approximation neglects the variation of substrate Fermi potential as a result of extra implant. Yeah, that is true. We neglect the variation of Fermi potential as a result of extra implant. For a p-channel, we show one example, numerical example. For a p-channel metal oxide semiconductor, suppose the threshold voltage has been designed to be minus 1.16 volt. Now it is needed that we need to make it more negative, from minus 1.16 to minus 2 volt. That means make it negative by amount of 0.84. Determine the type and amount of channel implantation which are needed to achieve this. Obviously, as it is required to make it more negative, so what we do, we have to execute ion implantation but involving N-type impurities, okay, or pentavalent impurities. Why? Because if you do that, the donor ions will become positive, okay, at the time of operation. So that means it is required, it will be obvious that the corresponding threshold voltage will be more negative because it has to balance out. On the gate side, it has to be more negative. So given the gate oxide capacitance per unit area is 5.4 into 10 to the power minus 84 farad per centimeter square, we are asked to calculate the amount of channel ion implantation necessary to achieve VTO equal to minus 2 volt. That means to cause a decrease in magnitude by 0.84 volt. Okay, so you can easily calculate it out from minus 1.16 to minus 2 volt. That means it is required that delta V equal to 0.84. Okay. And what is the other requirement? It is required to find out Ni. That means how much ions per centimeter square needs to be bombarded into the channel. Let Ni be the density of implanted N-type impurities. Assume that all implanted impurities are electrically active. That is, each ion contributes to the depletion region charge. then the change in VTO equal to this, or Ni equal to just Cox into delta VT0 by Q, that is 5.4 into 10 to the minus 8. So it is required that 2.84 into 10 to the power 11 ions per centimeter square is the required concentration of the N-type impurities. Normally, apart from enhancement type MOS transistor, we also require the use of depletion type normally on N-channel MOSFET. This we shall find in the actual circuit operations like PLA, okay, or even inverter when we shall study about that. So let us introduce ourselves to depletion type. What do you mean by depletion type in a transistor, in MOS transistor? It means that even though VGS equal to 0, that means the gate and source or gate and substrate potential are same, still a channel exists and current can flow. Okay, so for NMOS transistor, VTO of NMOS transistor can be made negative using selective ion implantation. Thus, a conducting channel exists for such a transistor at VGS equal to 0, enabling current flow between its source and drain terminals, as long as VGS is greater than the negative threshold voltage, right? As long as VGS is greater than the negative threshold voltage. Okay. So in general, the depletion NMOS transistor has got negative threshold voltage, and depletion type PMOS transistor had got positive threshold voltage. Several practical applications exist for such depletion type N-channel transistors in the design of MOS digital circuits, and these are the typical circuit symbol. You see that the thickened line indicates that already a channel is formed, even though gate and source are at same potential. Even though VG is equal to 0, still a channel exists. If you have to make the channel disappear, you have to make gate to be negatively biased with respect to source. Okay. Also, that means this thickened line is there in vertical line. It means that this accounts for depletion mode in MOS transistor. Now see, with the variation of source to body bias, okay, the threshold voltage will be likely to change. Now let us see the range of change of the threshold voltage. So consider the N-channel MOSFET process we have seen earlier. In various digital circuit applications, VSB equal to 0 is not possible. How does this VSB, that means the source to body voltage, not being equal to 0, affect the threshold voltage of the MOS transistor? That means how much change it will lead to in the threshold voltage of the MOS transistor. Take again the data like acceptor ion concentration happens to be 10 to the power 16 per centimeter cube. Gate oxide capacitance per unit area, that is 7 into 10 to the power minus 8 farad per centimeter square. And the body effect or substrate bias coefficient in this particular example happens to be, okay, root over 2q Na epsilon Si. You put in the value. Q is 1.6 into 10 to the power 19 coulomb. Na equal to 10 to the power 16. Okay, and epsilon, the gate dielectric constant of silicon is 11.7 multiplied by free space permittivity. Put in the value and gate oxide capacitance per unit area. It is also given. You calculate gamma to be 0.82. Note the unit of gamma, that is V to the power half. Okay, because of the fact that when you write in the expression of Vt, that is Vt0 plus gamma into root over some voltage. So as the overall thing has to be same unit as volts, and this is having square root of volts, so gamma unit will be root over B, okay, or B to the power half. So you put in all the values. The zero bias threshold voltage in this case happens to be 0.4. Then this will be the trend. If you keep on varying VSB, accordingly the threshold voltage will vary. So here we show, actually we have first calculated for various values of VSB. For 0 it is, for VSB equal to 0, the value of VT0 is 0.4. Then it will gradually increase as you increase VSB. So as you increase VSB over the range 0 to 5, 0, 1, 2, 3, 4, 5, you will get the values and you can draw a fitting curve to show the variation of threshold voltage. So starting from 0.4, it can vary as much as 1.6 volt or 1.7 volt. Okay, threshold voltage is found to be almost about 1.3 volt. Now, substrate bias effect is almost unavoidable in most digital circuits. See, not all the NMOS transistors, you will find that the source and body are both at ground potential. Okay, it goes without saying that all the NMOS transistors used in the circuit, for all the NMOS transistors, the substrate or body are definitely connected to ground potential, the most negative potential in the circuit. But the source need not always be connected to substrate potential, that means grounded. For pass transistors in particular, okay, source and body cannot be at the same potential. Source will be positive with respect to body. So for them, it will, you have to calculate the VT separately. Okay. And here, as we find that the range of threshold voltage is between 0.14 to 1.7. So minimum voltage required to drive the transistor should be above 1.7. So let us be at least 2 volt or so, right? Next, what we see, okay, this is briefly we note. As we come to take into account the transistor, say NMOS transistor, it consists of two isolated islands of source and drain. Okay, so as the majority carriers flow from the source to drain, it means the conventional current is flowing from drain to source. Okay, so VDS is there. That means the drain is positive with respect to source. Now, in general, the channel becomes tapered towards the drain. It is due to the reverse biasing effect of the channel. Okay, this you all know. Just we are seeing that the expression for saturation current is this: mu n COX by 2 W by L prime into VGS minus VT0 whole square. Okay, mobility of the N type carriers. COX gets capacitance per
Sir,
unit area. Yes, yes.
sir,
Yeah, any
can you
doubt?
please, yes, sir. Sir, can you please explain how did we get that range of threshold voltage?
Okay, okay, yeah. Right, thank you. So, come to consider this. All of you know that the generalized threshold voltage can be related to a zero bias threshold voltage plus, if you have to consider when in general the source and body are at different potential. Remember that for n channel transistor, okay, we have to consider p type semiconductor or p type substrate. So source in general is at positive potential with respect to body, while for PMOS transistor, recall that it involves the use of n-channel substrate. So source is in general negative with respect to body for p-channel transistor, right? In general, we are considering the n-channel transistor. So for this, source is at positive potential with respect to body. So then this will involve the total expression. Generalized expression will involve the presence of zero bias threshold voltage and involving gamma. That means the substrate bias coefficient. We have to consider this sub expression. Okay, that you have to keep in mind. Now, VSB, the source substrate bias potential, can vary over the range 0 to 5 volt. Now, this why it happens. You see, if you have got stack of transistors, suppose one transistor is there, for which the source and body are shorted. Okay, so for this VSB equal to 0, fine. But if you consider some transistor which is connected to say drain of that particular transistor, so source and drain are at, that means the drain of the bottommost transistor is connected to the source of one transistor. Then the drain of the second transistor is connected to the source of the other transistor. So we see that if you consider stacks of transistors, the sources of the transistors will be definitely at positive potential with respect to the body or substrate. Okay. For all the NMOS transistors, please remember that for all NMOS transistors used in a particular circuit, okay, the body or substrate is always connected to the positive, sorry, the most negative potential, that means the ground connection, the circuit ground. But the sources need not be connected to ground. Sources can be incrementally higher and higher. Okay, as you have stacks of transistors, right? So then that means the levels of transistors, several levels of transistors you have got. Okay, starting from the bottommost transistor. For the bottommost transistor, it is source and body are shorted. But suppose you consider, okay, a linear array of transistors. Starting from the bottommost, you go up to several layers. Then the source of the transistors which are higher up, definitely they will be larger than 0 volt. Okay, so you have to consider how much the VSB can vary, right? So if you take that practical applications, source and body voltage difference you have to take into account. Now, suppose for a particular circuit it is found that VSB can range from 0 to 5 volt. Suppose, then we need to calculate what can be the threshold voltage of the topmost transistor. Okay, that for that the VSB difference is maximum. Suppose it goes up to 5 volt. Just for the sake of example, I'm telling. Then the threshold voltage variation will be starting from 0.4 and it can be as high as 1.7. right? So for some transistors, it can be 0.4, the bottommost transistor, of which the source and body are shorted. Again, the transistors which are placed higher up, for them the threshold voltage will be higher and higher. Okay, right? So then you can have, for particular some transistor it can be 1.8, for some it can be between zero point 0.8 and 0.12, or maximum it can go up to say 1.77. Then it is needed that the minimum voltage required to turn on the transistor, the topmost transistor, of which the VT threshold voltage is say 1.7 volt, then you the range of voltages that would be meant for driving those transistors should be greater than 1.7. So let us say that the minimum voltage should be 2 volt, right? That's what I'm telling. Okay.
Sir, here are we taking the range of VSB up to 5 volt because maximum supply will be 5 volt? Or sir, there is some other
Actually,
reason?
not like that. For if we take the gate voltage to be zero point 0.4 volt, you see that for some application, gate and drain may need to be shorted, right? So drain is connected to 5 volt, then gate is connected to 5 volt. Yes, that means you can take the maximum range to be 5 volt or even higher, even higher. Okay, that means it is assumed that in general, you see, source is at a lower potential with respect to gate. So that means maximum voltage should be definitely above 5 volt, right? Because we are taking into account the source voltage, right? So VSB, if VSB equal to 5 volt, then definitely the power supply voltage should be above 5 volt, right? At least say
Okay,
if
sir.
you consider 1.7, so it should be about a 7 volt or 8 volt, something like that, not 5 volt. Okay. That means
Okay, sir.
when the range is 5 volt, then the power supply will go beyond 5 volt, at least say 8 volt or so on. Right. So this is just a what you call a numerical problem. In actual voltage, how much that will depend on the application. Okay. Right. So channel length modulation. Okay, channel length modulation we are talking about. That means you see the channel, the width of the channel is maximum at the source end. Again, as you progress towards the drain end, it becomes lower and lower. This is because of the reverse biasing effect of the PN plus junction. Please recall that I have not written for a NMOS transistor, you have got lightly doped P-type substrate here. Okay. And N plus source, N plus drain. So you have to consider PN plus junction here, PN plus junction there. And of course, as the body is connected to 0 volt, so this PN plus source junction and PN plus junction are reverse biased. If the gate and source are shorted, then this is actually zero biased. But PN plus junction, if we consider involving the N plus island, drain island and P-type substrate, definitely it is reverse bias. Now, as a result of this reverse bias PN plus junction, okay, there is a reverse biasing effect. So the channel width becomes constricted as you proceed towards the drain. When there is current flow, remember that the drain end side, the channel width is shorter compared to that of the source end. Now, let us assume that the VGS is fixed, but gradually you are increasing the drain potential with respect to source. Then what happens? For very small drain to source potential, remember, the circuit connection is like that. Gate to source potential is fixed, but drain to source potential you are gradually varying. Okay, starting from very low potential going up and up. For very low VDS, the circuit, the transistor happens to be in linear region. Okay, but as you increase VDS for the value VGS minus VT, that is at the onset of saturation, when the transistor passes from triode or linear or resistive or non-saturation region to saturation region, at the onset of saturation, you have got VDS equal to VGS minus T, the overdrive voltage. Okay, so at that point, the tip of the channel lies at the drain end. Okay, that means you have got the pinch off point happening at the drain side, right? Then gradually, if you keep on increasing VDS beyond VGS minus VT, then what will happen? The pinch off point will travel towards the source end, right? That's what we are trying to introduce. So the figure that you have drawn will correspond to the case when VDS is above the minimum potential between drain to source that is required to cause the transistor to go to saturation. Then what is the expression that we can expect? Then the saturation current will have this. See, while we write L prime means the capital S is the original channel length. But as a result of increasing VDS above VGS minus T, so the tip of the tip of the channel can be away from the drain end. So there you get the what you call no channel at all. But then the question arises how the current flow will be maintained. Yeah, current flow will be maintained in this fashion that the carriers travel over the channel as they come into this point. Then under the effect of field, okay, under the effect of electric field, they will be swept across the what you call the channel, the what you call the zero channel. We call it to be the lack of the channel. So this is what this p type substrate. This is somewhat charged. Okay, you have got the depletion area charge, but the carriers can be swept across this what do you call the this what where channel where there is no channel, but then still it can move over to the drain by the means of field effect. Okay, and what is L prime? L prime is the effective length of the channel, the electrical length of the channel. Then L minus L prime or delta L is the extent of the depletion region at this point. Okay, right? So we write in this fashion. Delta L is the length of the channel segment with zero inversion charge. That means here there is no channel, but still the current flow is not impeded. That is due to the effect of the field. Now we rewrite this expression in some form. You see, we bring in the original channel length L, then it will become L by L prime. And this we rewrite as L upon L minus delta L. What is this delta L? Delta L is in the as a consequence of increasing VDS above VGS minus T. This is called the channel modulation effect. Okay, and let us express it in a bit more detail. That means here we see for uh, we have to bring in to the to consider the what you call the channel modulation coefficient lambda. How it is coming? Let us see. So when applied, I've written in details for your understanding. When applied drain bias exceeds the minimum required BT sat, which is one, then the drain current continues to increase as the pinch off point progresses towards the source. And voltage drop across the channel is this VDS equal to minus VG. Then where there is no channel, the voltage drop will be just the difference of VDS minus VDS sat. Okay, right? And the additional voltage drop will appear across the narrow depletion region at the drain end. Note that the width of the depletion region, that means delta L, if you have to consider this, if you consult any semiconductor device book, you will find that the this width of the depletion charge, width of the depletion region can be found out by considering different concepts, particularly the contact potential or the diffusion potential of this PN plus junction. So what is this? Let us call it to be V0. Okay. V0 is the contact or diffusion potential. Then it is 2 epsilon into VDS. This expression, just if you I have written for your reference, okay, details how it is coming that you need not know, because you can consult any semiconductor device book, it will be appearing there. What is Na? Na is the acceptor concentration. Nd is the donor concentration of the drain region. Okay. And in general, V0 is smaller compared to VDS minus VD sat. So normally, the this width of the depletion region is proportional to root over VDS minus VD sat. But we can simplify the analysis furthermore. That means let us take that this delta L or the relative decrease of the channel length as a result of high drain to source potential. Let us call it that relative means delta L by the original channel length. Delta L by L is proportional to VDS. Yes, this is very simple, but very practical. Okay, that is delta L by L is proportional to VDS. Then we can write delta L by L is equal to the proportionally constant is a lambda. Lambda is called the channel uh, length coefficient, or let us say channel modulation coefficient. Okay, channel length modulation coefficient. Normally, lambda is having the value equal to a few tens of volts, say 0.1 volt. Okay, 0. The unit of lambda will be, you see, lambda into VDS. Okay, you write it in the fashion. Look at the expression. Okay, 1 plus lambda VDS. This should be unitless. That means the unit of lambda is volt inverse. Okay, so 0.1 volt inverse or 0.05 volt inverse, something like that. One can simplify the analysis by introducing lambda. That means instead of writing this 1 upon 1 minus delta L by, let us write it to be 1 minus lambda VDS. If you write it, then from binomial theorem, what do you do? This is equal to 1 plus lambda VDS. And as lambda is much less than 1 in general, so we just take the second term, 1 plus lambda VDS into this. So here what we see, okay, that means as the transistor passes into saturation, uh, theoretically, saturation means that the drain current should remain constant, but it is slightly having a positive slope, even though the transistor has passed into saturation. That is the underlying thing of this discussion. Okay, that means because of the presence of the term 1 plus lambda BDS. But for normal calculation, we'll tend to neglect the channel length modulation. Okay, if you have to be very accurate, then we need to consider the channel length modulation coefficient. Clear? So in general, this is the correct expression. That means the expression for saturation drain current involves the mobility of n-type carriers, gate capacitance per unit area, then the aspect ratio W by L, gate voltage, zero bias threshold voltage, and then lambda you bring into account for high value of drain to source voltage, much above VGS. Okay, right. So this is a complete expression. Now, why do we study this? Yeah, why do we study this? Now we have to move over to, yeah. Let me next continue with this. So far, I believe not much difference, not much what do you call the difficulty is there. Let me now introduce you to yeah. So yeah, all of you can see it. Yeah. Now, so channeling modulation we have seen, right? And we need to calculate. There are important parameters to consider in most transistor. For in most transistor, we are seeing similar will be the consideration for PMOS transistor. Now, see the normally the drain current we saw in general, the drain current is a function of the gate to source voltage and the drain to source voltage. Also, the substrate bias, if we consider, then the drain current becomes a function of three voltages: VDS, VGS, and VSB. Okay, why? Because within this the VT is there, the threshold voltage, and VT is a function of VSB, the source to body bias. Right? To account for non-zero VSB on current characteristics, we need to consider this. Gamma assumes importance, right? And here this is for the uh, linear region expression. This is for the saturation region. Now we show you the N-channel MOSFET typical circuit uh, symbol. Okay, so if you show the inward arrow, okay, it means that we are talking about the N-channel transistor. Okay, and if you see outward arrow, then it means the p-channel transistor. This is a normal uh, symbol. Okay. Acha, parameters involved in the current voltage. Please note down, dear friend, that what are the important parameters? You have got to calculate the zero bias threshold voltage VT0, then substrate bias coefficient gamma, channel length modulation coefficient lambda, and transconductance parameter. That means mu n into Cx into W by L. How to calculate that? For that, you need some experimental setup. Okay. Please note that we need some experimental setup. First of all, assume that we are biasing the NMOS transistor into saturation. How do you do that? Connecting gate and drain together. Okay. So then VGS, you know that VDS becomes greater than VGS minus VTO, because VT threshold voltage for NMOS transistor in general is positive. So VDS, if you gate and drain are connected together, obviously VDS is greater than VGS minus VT. So whenever gate and drain are connected, obviously the transistor is biased in saturation. Now, why we need to bias it in saturation? The reason is that, okay, in that case, you have got the parabolic curve. Okay, so that means you get ID sat equal to Kn by 2. For the timing, note, dear friends, that we are neglecting the channel length modulation coefficient. So we take lambda to be 0 for simplicity. ID sat equal to Kn by 2 into VGS minus VT whole square, right? Okay. In that case, you take the square root of the current, it becomes root over Kn by 2 into VGS minus VT0. So if you plot the square root of current as a function of VGS, so it mostly becomes a straight line, linear. Okay, and if you plot it, yes, yes, yeah. Any doubt? Yeah, please.
Can you please why lambda 4?
Lambda equal to the y. Yeah, yeah, yeah. That is to make matters simple. That means lambda is taken to be 0 because of the fact that in general lambda is much less than unity. So what you do actually when you are calculating the other parameters, lambda if you leave out, lambda will come later. Yeah, lambda will come later when VGS will be taken to be very small and VDS for two values, for two different values, we shall consider the current, and then from there we'll try to calculate lambda. But when we are busy calculating the other parameters, namely the zero bias threshold voltage VT0, substrate bias coefficient gamma, and also the transconductance parameter, it is better to what do you call, ignore lambda for the time being. Okay, right. That means let us assume that for the transistor is in lambda, when we need to consider lambda, we need to consider for very high value of VDS, much above VGS. But suppose the transistor has passed merely into saturation, and for typically lower values of VDS, that means we can assume that the current curve is mostly uh, parallel to the voltage axis. Okay, that means the slope of the current curve is not much prominent. It will become prominent if you increase the drain to source potential much above the VGS minus T value. So for drain to say here you have got, you can control the drain to source value, right? As you can clearly see, this is the experimental setup, dear friends. Okay, that means gate and drain are shorted. There is an ammeter to measure the current, and you have got a variable potential source to vary the drain to source potential. Now, always VGS equal to VDS, but suppose VDS is a smaller value. That means VGS minus VT. Okay, VDS is slightly larger. Okay, in fact, VGS equal to VDS. So for relatively small value of VDS, okay, as the current curve, you note down that it will be just in saturation, but not into deep saturation. Okay. For that, we need a separate setup. Okay. That means you can keep VDS to be much above VGS. But here actually VDS is just equal to VGS. Okay. So for practical matter, it is not in deep saturation, mind you. All of you can see this experimental setup. No. If you connect G and D together, you cannot make the transistor go into deep saturation. However high you make drain to source voltage, the difference between VDS and VGS is only VD, right? All of you note, right? Because VDS and VGS are equal. So what is the difference of VDS? That means VDS is greater than VGS minus VD. That is satisfied. But say, let us say threshold voltage is not much high. So in the also you have a means to control the threshold voltage, right? Because you have got another potential source here. Okay, so if you can make the transistor merely in saturation but not in deep saturation, then you can neglect lambda, right? You have got it. I will, it's clear, right? So that means for practical matters, if this, in order that this equation be in force, we make this experimental setup where you can justifiably neglect lambda. Okay. So now you see, if you do so, if you tend to plot the square root of current as a function of the gate to source potential, then obviously you have got a linear plot. Okay, sorry, you have got a almost straight line plot. And at this point, you are varying the threshold voltage. Suppose VSB equal to 0. This variable, I'm sorry, I should have pointed a variable symbol. So symbol for a variable source. That means if you put a arrow here, VSB can be equal to 0 or VSB can be made more positive, right? So in that way, what you can do, in that way,
Excuse me, sir.
yeah, yes, yes. Any doubt, please let me know. Yeah,
For this
yeah.
setup, it's shown in the figure, no? So, is it possible to means to go to this experiment or whatever it is to in deep saturation?
Yeah, normally the difference differentiation means is VDS will be much above VGS minus T, right? VGS minus T is the onset value of the drain to source potential. Now, as gate and drain are connected to, gate and drain are connected, that means what is the maximum difference of VDS and VGS? That is restricted to the value of threshold voltage, right? Because as drain and gate are connected, what is the maximum difference you get between VDS and VGS? Okay, that is maximum threshold voltage, right? Get it? And threshold voltage can be say for typical 5 volt source. Okay, threshold voltage can range from say zero point 0.8 volt, 1 volt, 1.2 volt, 1.5, maximum 2 volt, right? Normally, I'm just saying normally. So
Yes.
there, the difference of drain to source potential and the onset value, that means VGS minus VT, is not much. So that means as you are merely in shallow saturation, okay, so there the current slope is not much, okay, is almost parallel to the voltage axis. But suppose you allow drain to source potential to be much higher above VGS, then you should not uh, should not connect gate and drain. We'll show it next. Okay, that
Yes.
means what
Because if
experimental
you
setup.
increase,
Yeah,
yes, sir.
yeah,
Because if
yes,
we increase the drain voltage, so it automatically increase the gate voltage also.
exactly, exactly. Very good. As gate and drain are connected together, however high you make the drain to source potential, gate potential is also correspondingly increasing. So it is not possible to
Yes.
take the transistor deep into saturation and allow for the
Yes.
what do you call sizable slope for the current. Good. Thank you, Punendu. And another thing you see here, this is also you can say that I have done some mistake and I admit. That means VSB, is it not? Body is always grounded, but the ground should not be here. Ground should be here. Okay, right. I'm sorry for that. You have noted for. I think all of you have noted that you have got a variable potential source. Normally, the body is connected to ground, but here I am showing the source to be grounded. That is mistaken also, right? So if you have to make the zero bias threshold voltage, yeah, zero bias threshold voltage is the least value possible for threshold voltage. But if you have to take VT to be above VT0, then source should be made positive. But here by mistake, I am showing source to be grounded. Please, my apology. The body is connected to ground, not the source. Okay. The positive pole is connected to this battery is connected to source, but the negative pole should be grounded. I think you have noted it, right? Okay. So what we show here is that we are plotting the square root of current as a function of gate to source voltage for let us say two typical values of the source to body. For one, VSB is 0. For another, VSB is some positive value. Then the other curve is slightly away from this curve towards the positive voltage axis. And why you can easily understand. See, if you look at this, if you look at the second graph, that means root over IT equal to. So this is equivalent if you consider a y equal to mx plus c curve. So root over kn by 2, it is the slope of the straight line, and the intercept will be intercept will be on the current axis. It will be root over kn by 2 into vt0. Okay. Okay, right. So that is negative actually, right? Negative intercept. We are not showing it. But on the if you normally when you are this you are measuring by ammeter, so it is impossible to get the value of any current when when you bring down the VGS as small as possible. Okay, but still what you can do, you can extrapolate. See, for the obtainable current, you can these points are the typical experimental points. Okay, normally when exactly VGS equal to VT0, you get zero current. However hard you try, you will not get any current value for VGS particularly equal to VT0. That means VGS equal to, that means when channel starts to appear, you will not get much current, means measurable current. You have to bring VGS to be somewhat higher up above threshold voltage so that the measurable current can be flowing. So these points are showing somewhat above the voltage axis. But what we can do, we can extrapolate the curve backwards and assume that it is forced to meet the voltage axis. Then the intercept on the voltage axis or the horizontal axis will correspond to the threshold voltage. So this is for the zero bias threshold voltage, and this is for the non-zero bias threshold voltage. You get two values, say VT0 and VT1. Then why do you do that? Because from here, by applying this is a very important expression for you by now, so that means I can find out gamma equal to Vt for a for some positive value of source to body bias minus the zero bias voltage divided by this. Okay, and suppose I know the value of the electrostatic Fermi potential of the p-type semiconductor. Suppose I know it is say 0.25 volt or 0.35 volt. Okay, actually minus negative 5fp, if you know it is negative. So suppose we know the value, technology value, say it is given to minus 0.25 volt or minus 0.2 volt or minus 0.3 volt. Then I know the value, and VSB is within my hand. So as experimenter, okay, we are doing the experiment. This we can control, this we can control. Okay, so other values, some technology parameters should be given.
Sir,
Yes, yeah, any doubt? Yeah, yeah,
so the root ID VGS plot
yeah.
for VSB equal to 0,
Mm.
why it is not continuous?
Okay, yeah. Root over ID for VSB not equal to 0, no? As
No,
far as
sir, root over ID versus VGS plot when the VSB is 0, that
yeah.
plot, why it is not continuous?
Acha, continuous means you mean to say, suppose VSB equal to 0 and VDS can go, I mean, you see how much current is allowed to pass for a transistor, that is provided by the manufacturer. Okay, say it is given to say 5 milliampere or 10 milliampere for something. So we have to see that drain current does not exceed that limit. So we have to stop at some point of the drain to source potential. And as far as the as far as the lowest value goes, it can be as low as the threshold voltage. Suppose the threshold voltage is a point, say 1 volt. Okay, then the least value that you can bring up and you get measurable current will not be 1 volt, it will be somewhat higher, because if you have VGS to be exactly equal to VT, the channel has just started to appear. So if you remember the plot of the uh, output drain current versus VDS characteristic, if you look at if you consider ID VDS characteristic, it starts from a very small value of VDS and it proceeds. So for the for VGS equal to VT, you see the curve almost coincides with the voltage axis. And for VGS above VT, suppose VT equal to 1 volt, then VGS should be at least say 1.5 or 2 volt. So we get a measurable value of current. But VT equal to exactly VG, the current is almost negligible. That's what we say, that this curve, this curve may not touch the voltage axis experimentally. So that you have to do by extrapolating the curve. So for example, for value of VGS equal to 1, suppose I'm saying VT0 equal to say 1 volt. Okay, then VGS equal to 1 volt, you will not get any current. You cannot measure. Again, how do you measure the current? Ammeter. It is in our laboratory. What we do for our EG students, you can ask them that we keep a resistance, small resistance, and across the resistance we measure the drop, and from the drop we a voltage drop, and then we calculate the drain current. But with VGS currently exactly equal to VT, you will not get any current. You will see that the voltage drop is 0. Okay, so you have to bring it a bit higher up than the threshold voltage. So if this is 1 volt, let us say from starting from VGS equal to 1.5 or even 2 volt, you will get some measurable current. That's why these points cannot go right directly continuously up to the voltage axis. This you have to extrapolate. Okay, and also another point you need to keep in mind, that the VT0 that you get by this measurement may not match the exact value that is provided by the manufacturer, because there are certain what do you call assumptions that we are making, like neglecting the lambda and all that things. So unless we neglect the lambda, we cannot measure the other parameters. For measuring the lambda, we need a bit different setup where gate and drain will not be connected, will not be shorted, because there you have got the freedom to extend VDS much above VGS. But here, drain and gate are shorted, so always VDS equal to VGS. You cannot go away from that, right? Get it? Punendu and yeah,
Yes, yes,
Purito?
sir.
Okay. Now
And
you
sir,
see,
one more thing, sir,
yes, yes,
hello.
Yeah,
And
yeah.
sir, in that MOSFET diagram, when where you are has shown the bias of that source,
Just
body, gate, and drain.
yeah. Hey, hello Vivek, I am taking class actually. बाद में बातें करूंगा. हाँ, अभी क्लास चल. किसको किसको? आप मुझे ईमेल भेजा है क्या? साहू? हाँ? अच्छा वो कहाँ का स्टूडेंट है? मतलब ये इलेक्ट्रिकल? ओ ओ आपका पीएचडी स्टूडेंट है? हाँ? ठीक है, जरूर ऐड करूंगा. एक्चुअली अभी तो क्लास चालू कर दिया. ठीक है, कल से मैं ऐड कर लूंगा. हाँ, ठीक है. ओके, उसको बोलिए मुझे मेल भेजने के लिए, सो दैट आई कैन सेंड इन द चैनल लिंक का एमएस टीम्स का. ठीक है. सी सी श्योर श्योर श्योर. आप उनको भी मेल में रखिए. ठीक है, थैंक यू. ओके, ठीक है. गुड मॉर्निंग सर. ओके. Sorry, Ankit. Can you repeat the question? Sorry.
Yes, sir. Like the biasing voltages of that gate, source, drain, and body in the diagram you have shown.
Yeah.
Uh,
Okay.
sir, what is the problem in the biasing in that circuit?
Now, in this circuit,
Yes, sir.
yeah, once again, see, that means gate and drain are shorted. That means you will force the transistor to be always in saturation. That is for one thing. And next, what is your question? What is the problem in biasing?
So, like you told that the source, like in this circuit, the source is grounded and the body is connected to a
Oh
negative
yes,
potential.
yeah. Good. Yeah.
So,
Actually,
what is
by
the
mistake,
problem?
the problem is that problem is that you see, in general, for all NMOS transistors, the body or substrate are grounded. Okay, not the source.
Yes, sir.
Right. Only for the bottommost transistor in a stack of transistors, the source will be same as the body. Suppose you have got a stack of transistors. Say if you consider, uh, what do I say? Suppose
Cascode structures.
cascode structure. Yes, in analog you have studied about that, or even say NAND gate.
Stack.
Okay, we have got a
Yes.
series placement of involved transistor. Then the bottommost transistor only for that only source is connected to body. But as you go higher up, okay, suppose in suppose a 5 input NAND gate, then you have got a series placement of 5 transistors in the NMOS path. Then for the bottommost transistor, the source is connected to body. But as you go higher up, so second transistor, third transistor, the difference of source and body potential will be
It
increasing,
will
right?
rise.
Yeah,
Yes.
it will rise. So that
So,
by mistake, this ground should be in the body side, not in the source side. Okay.
no, sir, like I was just theoretically asking, like theoretically, is there any problem with this kind of biasing arrangement? Because the body is connected to the lowest potential. So, like I'm just
Yeah.
asking.
Theoretically, there problem. Yeah, you can tell me what is the problem. You tell me. I want the answer from you. Yeah, answer is that, see, for the NMOS transistor, body is what? P type and source is N type, right? So if you connect it to body and so then what will happen?
It will forward bias.
Theoretically, yeah, theoretically it is not
It
much
will
of
increase the threshold voltage, I think.
exactly. But normally, it's not much of a problem. Yeah, experimentally, this is a single transistor. Actually, yeah, you're right. In actual circuitry, you cannot make this connection.
Yes, sir.
Okay,
In
yeah.
act
Yeah,
theoretically, I was
you're right.
just
Yeah, there is
asking.
no problem because the PN junction will remain reverse bias because this is the N channel side, is the P channel side. So P is always more negative with respect to source. Yeah, there is no problem. I'm sorry, dear friends. Yeah, as you have got a single channel, as you have got a single transistor, there is no problem. Even though source is shown to be grounded, no problem. Yeah. So need not make any change. Because what I was worried is that I was considering a multiple channel transistor. Sorry, multiple channel circuit, but it is definitely not like that. You have got a only single transistor, so no problem. Even if you connect it to ground, no problem. The reason is that in field effect transistor, in order to make the field effect prominent, okay, you need to make certain PN junctions to be reverse biased, like the PN plus junction, which you are considering between source and body, which you are considering between drain and body. They should be, for all practical purpose, they should be kept reverse biased so that the field effect becomes prominent and not the not the BJT type of operation becomes prominent. And here it is not violating that. Why? Because source is a N plus junction, drain is N plus junction, and body is P mildly doped p-type substrate. So yes, this PN plus junction remains what do you call PN plus junction remains reverse bias, right? Is it not? Because P is connected to negative pole, N is connected. Yeah, it will not violate. So this will work. This will work. I'm sorry. I was just having in mind some multiple, like you said, cascode connection or so on. When we are considering those connections, then source cannot be grounded. Yeah, but as you, what is the objective of this measurement? Objective of this measurement is to measure certain salient parameters like VT0, then gamma, then the transconductance like mu n into COX, then later on lambda. So if we have to, if we are devising a setup only to measure the parameters, then this connection will never create any problem. So source for all practical purpose, we can connect it to ground, no problem. Yeah, and you need to make it so that the positive current can flow in this direction. Yeah, so no problem. Yes, this can be this can be connected, right? Yeah, there is no problem. Ankit, you are correct in pointing this out. Okay. So slope and voltage axis intercepts are used to determine K and N. So from the slope you get this transconductance parameter, whereas from the voltage axis intercept you get VT0. Okay, consider the extrapolated threshold voltage obtained from the voltage axis intercepts. Okay, use available VSB value to get the substrate bias coefficient like this. Okay, and also assuming a known value for the electrostatic Fermi potential of the p-type substrate. Okay, you can use this in your expression. Let me see a numerical problem on that. Okay, and this is the setup that we require for calculating lambda. Here also you see, please put your attention, please pay your attention. You see, gate and drain are no longer shorted. Why is it so? And also, uh, if you make it, if suppose you have got an idea, having measured the zero bias threshold voltage from this earlier experiment, also VT1, now you have got a fairly clear idea of VT0. Then if you get VT0 and then suppose VT0 is found out to be 1.3 volt, then you keep VGS to be just 1 volt above that. So in the test circuit for measuring the channel length modulation, this is the second test setup, which is merely to help us calculate the lambda, the channel length coefficient, channel length modulation coefficient. Okay, so in this test circuit for measuring the channel length modulation coefficient lambda, let us take, this is also not much required. You see, why do you keep it? Suppose you have got an idea of BT0 from the previous experiment. Say BT0 is found out to be 1.4 volt or so. Then you keep VGS to be 2.4 volt. Okay. Also choose VDS to be sufficiently large. Here you can make VDS independently large and large compared to VGS because drain and G are no longer shorted. VGS you just keep it to be sufficiently small so that easily you can make the transistor biased in saturation and you can take it deeper into saturation. Okay. So you choose VDS to be sufficiently large so that VDS is greater than VGS minus VT. And here obviously VDS is much above 1, device much saturation. So measure the saturation drain current at two different drain voltages. Okay. Then what you do for one, you see if VGS equal to strictly VT0 plus 1, then become 1. So it will absolutely become, we are restricting ourselves to this curve. That means the linear region, not to the, see, in the non-linear, in the linear resistive region, this is not linear. But as you, once you have come into the saturation region, and if you focus over this saturation region, then the curve can become precisely linear. Okay. That means if you bias VGS to be correctly equal to VT0 plus some constant, say 1, particularly why you make VGS equal to VT0 plus? Because this term becomes 1, so 1 square equal to 1. Then the overall curve becomes ID equal to Kn by 2 into 1 plus lambda VGS. That means precisely you are looking over this linear segment, not to the previous segment, right? Then what will happen? You just need to calculate the slope of this line, straight line, that is equal to lambda Kn by 2. Right? Slope is lambda Kn by 2 because the current equation will now become simply equal to 1 plus lambda Kn by 2 into, 1 plus lambda VDS into Kn by 2. Okay. So it is like y equal to mx plus c, where the m equal to Kn into lambda by 2. Clear? Okay. And as VGS equal to VT1, the current voltage equation becomes ID equal to Kn by 2 into 1 plus lambda VDS, so that the ratio of the drain current becomes very simple. Okay. Is it clear? I believe so. Okay. Now, yeah, let us take one numerical example. Measure the voltage and current data for, measure the voltage and current data for a MOSFET, which are tabulated. And let us determine the type of device and calculate. Actually, let me take the attendance now. Yeah, just I believe that, yeah, download attendance list. Because this you have to take routinely, okay? Because, yeah, okay, yeah, just take two. Yeah. So you see the, let us say the numerical value. We are showing a table where in the leftmost column we are showing the gate to source voltage and drain to source voltage, because we are now referring to the previous experimental setup where gate and drain are shorted. Okay, and VSB we are modifying from 0 to 3, and then through the ammeter we are measuring the current. Those are in microampere. Okay, 97 microampere, 235 microampere, 433 microampere, 59. See, as you increase the VSB, the current value is falling. Okay, for the same value of gate to source. That is obvious, because uh, as you are making source positive with respect to body, what is happening? It is showing some reverse biasing effect. That means the barrier height is increasing for the carriers to move from source to drain. Okay, we talk about some potential barrier is there, right? So then this potential barrier is rising as you make source with respect to body. So more resistance the channel is offered. So that's why as you make VSB to be larger and larger, the current value is falling. From 97, it becomes 59. From 235, it becomes 173. From 433, it becomes 347. Please note down this, right? Now assume that the electrostatic Fermi potential for the substrate, P dash substrate is minus 0.3 volt, right? As ID, the drain current, gate to source voltage, drain to source voltage, all are positive, the transistor must be NMOS. That is your inference. Assume NMOS enhancement type NMOS, okay, which is in saturation as VGS equal to VDS. Neglecting channel modulation effect, saturation current may be written as this. So root over ID equal to root over Kn by 2 into VGS minus VD. Let VGS and be two pairs, be two current voltage pairs. Okay, then current pair. Well, so suppose we tend to take, say, take the first two row. Then root over ID1 by root over ID by VGS minus PD equal to root over Kn by 2. This is constant. So root over ID by VGS by 2 equal to root over ID2 by VGS by 2 equal to root over Kn by 2, some constant. And then what we do, we need to find out Kn by 2. So what we do component or dividend. You see, for your benefit, I have written here, if A by B equal to C by D equal to some constant K, then A minus C and B minus D equal to K, that is equal to, so A by B equal to C by D equal to A minus C by B. That is your school days knowledge. You can apply it. So root over ID1, this is equal to root over ID1 minus root over ID2 upon VGS1 minus. And these values, this provides us with a means to calculate the transconductance, the process transconductance. Okay. So what is that? Suppose ID1 equal to 235, ID2 equal to 97, VGS1 equal to 4, and VGS2 equal to 2. Then root over 235 minus root over 97 upon 4 minus 3. Okay. So this is root over Kn by 2. So what do? You square it up. 5.48 into 10 to the power minus 3 whole square multiplied by 2 will give me Kn. And note down the unit, dear friends. Here the current is expressed in microampere and the voltages are volts. So the unit associated with transconductance, okay, will become microampere per volt square, right? So unit you need to keep in mind. Okay. Also, you see that if you look from this, here I have written root over ampere by volt, or say root over microampere per volt. Okay, so if you square it up, it becomes microampere per volt square. Okay, and Kn equal to microampere per volt square, roughly equal to 60 into 10 to the power minus 6 ampere per volt square, or 60 microampere per volt square. So while calculating, please confidently put the units, and correctly you have to put the units. Okay, because as engineers, all the measurable parameters must have their associated units. Do not make a mistake of that. Okay, right. So extrapolated threshold voltage at BT0 at 0 per substrate is found by calculating the x-axis intercept. So here, for example, if you take any two, say, if you take the first row, here I need to find out the BT0. So what is VGS? That is 3 volt and ID equal to 97. Kn we have just now found out to be nearly equal to 60 microampere per volt square. So from any car, I find that BT0 equal to root over 2I by Kn, okay, uh, root over 2I by Kn, that will give you VGS minus VT. So if you how to find out VT? VT equal to VGS minus root over 2ID by Kn. Yes, and VGS equal to 3 volt here, ID equal to 97 microampere, 60. This is also expressed in microampere per volt square. So that means equal to 3 minus root over 2 into 97 by 60. That is roughly equal to 1.2 volt. So zero bias threshold voltage is found out to be 1.2 volt. Okay. Now we need to find the substrate bias coefficient gamma. First, determine the threshold voltage Vt at VSB equal to 3 volt. So determine the threshold voltage first. Similarly as before, here we have calculated the zero bias threshold voltage. Now, if you pay attention, let us say to the fifth row, where VGS equal to 4 volt, VSB equal to 3 volt, and ID equal to 173 microampere. Okay, then this becomes VGS equal to 4 minus root over 2 into ID by K, 2 into 173 by 60, and the units are there 1%. Dear friends, just permit me uh, just 2 minutes, 1 minute gap, because as the my bell has rung, I have to open the door of the house. Okay, just 1 minute. Please give me. Okay, look at this. I'm just coming back. Yeah, sorry. So zero bias threshold voltage is found out to be 1.2 volt. And now what is the value of VS? What is the value of VT when VSB equal to 3 volt? To calculate that, we can take either fourth row, fifth row, or sixth row. The values will be roughly same. Okay. So here, for example, we have taken the fifth row value. So for VGS equal to 4 volt and ID equal to 173 microampere, and we have calculated the transconductance. So what should be the value of VT? Okay, you can calculate it like this from this expression. That means VT equal to VGS minus root over 2ID. So what is here, for example, VGS equal to 4 volt and current equal to 173 microampere and 60 microampere per volt. We have just now calculated transconductance. So 4 volt minus root over 2 into 173 by 60, right? So this is equal to 1.6 volt. Now, having found out threshold voltage corresponding to VSB equal to 3 volt, okay, now we can calculate the gamma. So, as with a given value for the electrostatic Fermi potential, that is 0.3 volt. So here all the values are given: 1.6 minus 1.2, okay, and 2.5f equal to 0.6, 0.6 plus 3 minus 0, roughly equal to 0.36 volt per v to the power half. Okay. So this here actually lambda we are not asked to calculate, but lambda if some other given data is there that for two different values of VDS you get the values of drain current, we can calculate it. That means keeping the VGS value same, okay, or rather fixing VGS to be equal to VT0 plus 1. And if the data is given to us, we can easily calculate. Okay, then there is no doubt about that. Okay, thank you. Actually, next, okay, till now I believe there is no doubt. Okay, so then we pass over to another topic. Let's say MOSFET scaling. Okay, now with the relentless progress in technology, what we want to do, basically, we want to increase the packing density of the chips. That means we want to accommodate as many transistors as possible on a given silicon wafer. And for that, it is obviously required that the dimension of the transistor should be smaller and smaller with the passage of time. And what do we mean by scaling? Scaling refers to reduction of the size. That is the MOSFET dimension. Note that the scaling of MOSFET transistors has grown aggressively, but not for the bipolar junction transistor. Okay, there can be some reason you try to find out. So refers to reduction in the size of the MOSFET transistor, that refers to scaling. But as you bring down the dimensions like the channel length, channel width, and also the particularly the oxide thickness. Okay, oxide thickness normally, if you relentlessly make it smaller and smaller, there is some danger with the high field effect that we shall see. Operational characteristics of MOS transistor can change with the reduction of dimension. Also, some physical limitations will finally restrict the extent of scaling that is realizable. That is true. You cannot go indiscriminately. You cannot reduce the dimensions without, thoughtlessly you cannot do. Two basic types of size reduction technology exist. Like one is the full scaling or constant field scaling. The second is constant voltage scaling. To describe device scaling, introduce a constant scaling factor is less than 1. Actually, when we say that, what we mean by say all horizontal and vertical dimensions of large size transistor are divided by 1 by s. Actually, this should be s greater than 1, right? If you suppose that means in today 2022, 2022, the dimension of a transistor is a 1 micrometer by 1 micrometer. In 2024, maybe we can improve it to so that the length of the transistor will go down from 1 micrometer to say 0.7 micrometer. So that means it will go down by a factor of 1.4. Okay, 1 by 0.7. So the scaling factor should be is equal to greater than 1. Anyway, that doesn't matter. You know that anyway the dimensions are going down. So all the horizontal and vertical dimensions of the large size transistor are divided by. If it has to divide by 1 by s, then s should be greater than 1. Sorry for that. Please make the correction. S should be greater than 1 to obtain the scale device. The extent of scaling depends on the fabrication technology and minimum feature size. Again, minimum feature size means you have to produce the transistors in a fault-free manner. So then our photographic resolution should be good. Okay, the actually in the design rules, you may have studied about design rules, that 2 lambda based rules. There is some minimum width of the polysilicon, minimum width of the diffusion, minimum width of the metal. Okay, and also when you are providing the transistor, you are fabricating the transistor. Okay, the minimum width, minimum length, all we have to maintain. But as the dimensions go down, okay, although it is not the fabrication is never done manually. Okay, because we will definitely do some mistake, and there can be, we can short the gate with the channel and all that. Okay, so everything is done mechanically, but still the photolithography, that means the photolithography means the how we are preparing the mask. Okay, several sets of masks are required, starting from the etching of the oxide, and then producing the source island, drain island. Okay, then the overlying gate metal. Okay, and everywhere. So the masks are to be made in a error-free way. For that, the advance in photolithography will matter. Okay, and definitely the fabrication technology. That means how good the diffusion furnace is there, how accurate you can do the, say you need to make n plus equal to say 10 to the power 19 per cc. So accordingly, the furnace has to be set up. Okay, so both fabrication technology and the advancement in photolithography will matter. and that will that two things together has made the scaling possible. Okay, now that you can get in our mobile phone, we can accommodate so many functions, including camera and so on. Okay, in a pocket borne device. It is because of the advancement in fabrication technology and also photolithography. Okay, that is the most underlying, and of course the design technology is there. Okay, hierarchical design technology. And here I take you a bit in the history. Okay, so starting in 1985, say feature size of 2.5 micrometer. Namely, feature size means that we are talking about the channel length and channel width and so on. Okay, so currently to 2013, this is also very old. So presently we are showing say 14 nanometer or 7 nanometer nowadays. Anyway, so a new generation of technology replaces the previous one every 2 or 3 years, and downscaling factor is of minimum size will matter about 1.2 to 1.5. Consider the proportional scaling of all three dimensions by same scaling factor. As the key dimensions of a typical MOSFET are reduced, doping density will get correspondingly increased. How? That we see just shortly. So in the following, that we are taking primed quantities indicate scale dimensions and doping density. One should understand the effects of scaling under the options. Normally, two options are there: constant field scaling or full scaling, and constant voltage scaling upon the current voltage characteristics of the MOSFET. Let us see. So I draw for your benefit just a three-dimensional figure where you see the gate is there, overlying gate. Okay, then oxide is between the gate and the big rectangular parallel pipette. What does it see? What does it show? The source island, drain island, and then the substrate. So roughly we have drawn. Now, when we talk about the full scaling or constant electric field scaling, we need to have the electric field to be same, although the dimensions are changed. And note that what is electric field? Electric field equal to minus dVdx. Okay. So if you have to keep the field constant, x is going down by a factor, say s. S is the scaling factor. The magnitude of internal electric field in MOSFET is preserved. Field is kept constant to avoid breakdown mechanism. That is very important. See, field induced breakdown is very critical factor to consider. Okay, field is kept constant to avoid breakdown and other secondary effect. Scaling leads to greater device. And what is the objective of scaling? The device density will grow up. Okay, and speed will be higher and reduce power. Ideally, these are the motivations. Okay, these are the objectives: higher speed and reduce power consumption. And performance improve, because higher speed means the transient characteristic will improve. Okay, that means rise time, fall time. Okay, the propagation delay time should be improved. Performance improvement due to reduced voltage swing and reduced capacitance. Now, normally we start with the basic Poisson equation: d2 v dx equal to minus rho by epsilon, and rho is the volume charge density. Okay, so you multiply with the electronic charge Na. Na is the ions per unit cubic centimeter, cubic micrometer, whatever. Now, if you integrate it, E equal to minus dV dx, you get this form: Q NaX by E. Now, obviously, as E, you see X will be replaced by X by S. And as you tend to have E to be same, obviously, Q you cannot change, epsilon you cannot change, but Na you can change. So you need to increase the doping density by a factor of S. Okay, so with the advancement of fabrication technology and photolithography, X will become say X by S after 2 years. So after 2 years, it is required that the doping density, doping concentration should be increased by a factor of S, right? So you see, that is indeed required if you have to go for constant field scaling or full scaling. As distance by length is scaled down, as distance or length is scaled down by S to maintain same field, Na, that means the doping density, ND also needs to be increased by S. Consequently, charge density is also increased by S. Is this clear? That means charge density also increased by S. And you see the various other parameters like depletion region, charge Qj, it is given by this. Okay, so dVdx, that means you see, in order to maintain constant field scaling, the voltage is also coming down. Oh, the voltage is coming down. That means X goes down by S, the voltage also coming down because dV dx, right? So here within the square root, you see voltages are getting down, and this is going up a square by S, and so this is become so after all, what do you get within the second bracket? Sorry, within the square root symbol, there is no change. You see the voltages are going down by S. This is coming up by S, and product of two doping density here in the denominator, single doping density. Okay, so no change is there, but outside you see the area is there. Here two dimensions are there, length and breadth. So this becomes changes. So depletion region charge now uh, becomes decreased by a factor of a square. In fact, I have written for your benefit. So charge decreases by factor of a square. What about depletion region width? This is also, you can see that within this there is no change. Uh, it decreases by S. Why? Because it is Na plus D. Okay, this is singly, this is quadratically. Okay, so this becomes a square, and this is S by S. So S cube, S by S cube, it becomes 1 by S square, right? 1 by S square, as it comes out of the root, it becomes 1 by S. So depletion region becomes changed, smaller by a factor of S. Maximum electric field remains unchanged. So you can verify all this. Now you see the gate oxide capacitance. What about this? See, first of all, capacitance per unit area. We talk about gate oxide capacitance per unit area, COX. So what is that? Whenever you write COX, you see C prime OX means after the scaling has been performed. That is epsilon OX by T prime exponent. Epsilon OX does not change, dielectric constant, but TOX becomes changed by factor of S. In fact, if S is greater than 1, say 1.4, 1.3, so it becomes S into CX. That means capacitance per unit area will increase by a factor of S. But what about gate oxide capacitance? Now that you are multiplying this by two dimensions, length dimension, okay, it becomes decrease. So gate capacitance decrease. Although gate capacitance per unit area increases by a factor of S, the gate oxide capacitance, that is when gate capacitance per unit area multiplied by area, cross section area, you get it to be decreased, scales down by S. This is beneficial. This will improve the transient operation of MOSFET. So one benefit of constant field scaling, you can indicate now that the overall capacitance is getting decreased. So it improves the transient operation of MOSFET. ওই ক্লাস নিচ্ছি, একটু বাদে ফোন করছি বুঝলে, এই 10টার সময় ক্লাস শেষ হবে। হ্যাঁ, ঠিক আছে, ওকে। So you see that the overall capacitance decreases, right? So that improves the transient operation of MOSFET, right? An effect of full scaling on IV characteristics of MOS transistor is that aspect ratio W by L is unchanged, right? Why? Because W comes down by a factor of S, L also comes down by a factor of S, so no change. Now, what about transconductance? See, by and by, you see what is the effect of scaling on different physical characteristics. Transconductance, you see, is becomes mu epsilon by T prime X W prime. So all the prime quantities will result after the scaling. That means 2 or 3 years down the line. So T prime OX will become TX by S, W prime will become W by S, L prime will become L by S, right? So you see these three parameters will be changed by factor S. Ultimately there will be S in the numerator. So it means the transconductance has increased by a factor, scales up. Okay. Now you consider its effect on the current. So linear expression of current is K prime N by 2 into 2 into voltage. And so this will become S K N by 2, and K prime we have seen. So K prime will become S K N, and then voltages are there, and voltages come down by a factor of S for constant dVdx will be 1 by S square. So ultimately, I see that the current will go down. The magnitude of current will go down as a result of constant field scaling. And similarly, saturation current also, it will be like that. And what about power dissipation? Power dissipation means voltage will come down by a factor of S, also current. Then it is very good. Power dissipation comes down by a factor of A square. Thus, full scaling or constant field scaling leads to reduction of power dissipation. As device area scales down by A square, power density per unit area remains unchanged. That is to be kept in mind.
Sir,
Power density means what? Power per unit area. Yes, yes. Yeah, yes, sorry, unit out. Yeah, let me know.
sir,
Yes,
over
who is
here,
this?
phi naught. Sir,
Yes, one, yes, yes. Yeah.
yes, sir. So over here, phi naught would change by ln s square, right? Means the built-in potential in depletion region, charge, and bit parameter. Hello.
Phi naught means we are pointing to
The
potential.
built-in
Where?
potential.
Yes, yes.
Sir, in expression of Qj and Wj, depletion region charge.
QJ and W. Yeah, 50. Yeah, 50 is there. Phi naught. Yeah. So 50 equal
Right.
to KT by log of NAND by N square. Yeah.
Yes, sir. So it would be just increasing by ln s square, right? So means it is not means then how do we just say that it would be changing by s or something like that?
Okay, what is the expression for phi naught? Is equal to KT by Q into log of NAND by A square, no?
Yes, sir. Yes, sir.
Sir,
Yes. Yeah.
sir, we can also look it at the built-in expression as half maximum multiplied by maximum field multiplied by the depletion width.
Yeah, Priyank, once again, tell me. This
Sir,
you are talking about. Yeah,
yes,
which
sir.
one? That potential?
Yes, sir. Phi naught
Yeah.
built-in potential. Sir, half multiplied by
Ah.
maximum field multiplied by the depletion width.
Okay. Yeah. Oh, yes. The simple geometric calculation. Yeah, right.
Yes, sir. The area
Yeah,
under the triangle.
right. Area under triangle. Yeah, in that case, you see, electric field remains same, whereas that dimension, that width will downscale by S. Yeah, right. Yes. So yes, Janison, in that case, you can explain that 50 is also coming down by a factor of S. Very good. Thank you, Priyank. So
Yes, sir.
this,
Got it.
that means the triangle area constellation will get you there. Yeah. So all the voltages will come down by a factor of S. Okay. Right. Yeah. So now you see the power dissipation. Power dissipation will be downscaled by A square, whereas the power density will remain unchanged because the power by area square. So area square means it will be downscaled by A square. So yeah, the power density will remain unchanged, but overall power will be improved. That is the very what you call say very positive aspect of constant field scaling or full scaling. That means not only the transient characteristics are improved, also the overall power is improved. That is very desirable, higher speed and reduce power consumption. Okay, and greater divergence. But the downside is there. Yeah, for practical circuit, you see, that's why we go for these are the benefits of constant field scaling, right? But for constant voltage scaling, you need to consider something practical. That means scaling of the voltages may not be practical in many cases. That means we are bringing down the voltage by factor of S. Within one technology, it is fine within MOS. But if you go across the technology, like for our what should I say, for uh, yeah. So if you have to consider the interface between MOS and TTL, nowadays we see that MOS packing density is larger than TTL, the BJT or bipolar junction transistor technology. But by BJT we cannot do without. BJT is unavoidable when you think of the interface circuitry or for enhancing the power, particularly the I/O interface. In the I/O interface, you must have studied about BiCMOS circuitry, where the internal your the logic computation is the logic kernel. It is made of MOS technology, MOS transistors, but for interfacing it to uh, uh, your actual user application, there you need to take care of the high power requirement. Okay, so then bipolar transistors will be unavoidable to use. They will be there always in the case of IO interface circuitry. Okay, within the chip itself, the MOS transistors will you can work, and there you can go for constant field scaling. But IO interface circuitry will always involve the use of bipolar junction transistor, because the current higher current requirement cannot be made by the MOS transistor. They have got limited what do you call that factor, transconductance. Okay, so transconductance of bipolar junction transistor is way above that of the MOS circuitry. Okay, so for high current requirement, high power requirement, high voltage requirement, we always have to use a mixture of TTL and MOS. Thereby, TTL, the voltage, you have to maintain certain amount of voltage. So although the internal voltages become smaller, the interface circuitry voltage will become larger. So we cannot go for indiscriminate scaling. Then it will require complex level shifter arrangement and multiple power supply. That is why at some point of time, voltage, it will be better that to do away with the need for multiple voltage supplies and complex level shifter arrangement. Sometimes what people do is that let the voltage remain the same. Although the physical dimensions are coming down, let the voltage remain same. We do not tamper with the voltage. So then there is another type of scaling. It is called constant voltage scaling. So let us just briefly see uh, what is the offshoot, what is the outcome of constant voltage scaling, how the physical characteristics are affected when we keep the voltage same, but reduce the dimensions of the length, breadth, and width, thickness. So all dimensions of MOSFET are reduced by S, but the power supply voltage and terminal voltage remain the same. In that case, you see field equal to given by V by X prime. So obviously field will be increased, scaled up by S. Okay, and if field has to be increased by S, from the expression of E, you see root over 2q by E Na Nd Na plus Nd, and this here you see it is required that the doping density should be increased by S square, not S. Earlier, for constant field scaling, it was required to increase N by factor of S, but here it is required to increase by factor of S square. So suppose 1.4 is there, 1.4 square is 1.96. So the cost of fabrication will be slightly increased if you go for constant voltage scaling, because more amount of doping you have to carry out, right? Achha, so here you see that means that means em prime will become S into em prime. So that's why unless this becomes increased by S square, you cannot achieve this. Okay, because within the square root it should be S square. So only if Na increases by S square and Nd increases, so S to the power 4 by S square. So then this becomes S square, because voltages will not be tampered with. Voltages will remain same. Thus, the doping density should be increased by S square to maintain charge field relation. That is important. Now, it is what is its effect now? You see, in the linear region current, okay, K prime by 2 will become, it is always, as it involves the dimension epsilon Ox by Tx into W by L. So obviously K prime N will become S into Kn. Okay, so that means overall current will now increase. So that means power dissipation will also increase, because voltage remains the same, but current increases by a factor of S. Okay, so power consumption per unit area will be increased S to the power 3. So that is the downside. Okay, power consumption per unit area did increase by SQ. Power itself increased by S. Earlier, for constant field scaling, we saw that power, in fact, is decreased by a factor of S square, although power density remains the same. But here we see that power increases by a factor of S, whereas power density increases by a factor of S to the power 3. So that means if you resort to constant voltage scaling for the power, it is increasing. And if the power increasing, the heating will increase, right? So that is not desired. Note that the power consumption per unit area increases by S to the power 3 due to constant voltage scaling. Now, constant voltage scaling may be preferred over constant field scaling due to practical reasons. in practical cases due to external voltage level constant. But constant voltage scaling increases drain current density and power density by a factor of s to the power 3. Such an increase in current and power can cause serious reliability problems for scale transistors. Yeah, electromigration we just briefly saw that it refers to if the here we see that the current will increase with the constant voltage scaling. So if current increases, the current density will also increase. That will lead to and if normally we as the fabrication engineer always try to make the width of the metal line, width of the division line uniform. But at some point of time, over a segment of the circuit, current density can increase too much. Okay, so then what will happen with the increase of excessive current density? Okay, the metal ions tend to migrate towards the direction of the current, and if it does so, it will lead to gradual reduction in the width of the wires, metal wires, particularly over some distance, very restricted amount of region, but eventually it may lead to simple discontinuity of the metal wire. That means the electromigration, why is it harmful? Electromigration means the migration of metal ions in the direction of positive current. Okay, when the current density increases excessively over a segment of the interconnections, then what happens? Eventually, at some point, at some what you call fixed locations, the wires can get snapped, can get discontinuous. So we understand that signal is flowing, but actually it is not flowing. So that can lead to what you call misinterpretation of data. Okay, and also hot carrier degradation. What is hot carrier degradation? Is that you see we are aggressively scaling down the dimension. So if the TOX, that means the oxide thickness, is also scaled down, then for constant voltage, you see what happens. Voltage remains same, but X is coming down. For constant field scaling, what was done? Voltage was also brought down by factor of is. Okay, so that means dVdx that remain constant. But here what happens? Constant voltage remains same, but X is going down. So that means dVdx it will increase, right? So field value will increase, and if the field value increases unchecked, it can lead to breakdown, field breakdown. That means something. Sometimes what will happen? Some that means gate we call eventually it can lead to some typical shorting of gate and the channel. That means even though VGS is below gate to source voltage, threshold voltage, but current starts flowing. That is also undesired. Okay, and hot carrier breakdown means with the increase of field, this can lead to severe what you call collision amongst the ions. Okay, oxide breakdown. Okay, that thermal stress, electrical overstress, all these things. So these are very undesired effect of constant voltage scaling. So as a practical what you call compromise, constant voltage and constant field scaling are both applied so over distinct segments. Say, for example, for the MOS transistors, we go about constant field scaling, whereas for the bipolar junction transistor, constant voltage scaling. Because otherwise, not only the difficulty of having to do with your what do I say, the need of multiple voltage supplies and voltage shifters will be required, level shifters will be required. But at the same point of time, constant voltage scaling, if you apply over MOS circuitry, it may lead to this undesired phenomena like electromigration, hot carrier breakdown. Even also you can read from your book that some undesired characteristic like undesired characteristic of one relentless downscaling is that DIBL, that drain-induced barrier lowering. Drain-induced barrier lowering means while the majority carriers for N-channel transistors, they have to move from the source side towards the drain side. Okay, so they face some barrier, and if the drain to source voltage increases, then even though the gate to source voltage is below threshold voltage, the barriers come down and the carriers start to move. That means this is also, you can say, an example of sub-threshold conduction. So all these things have come with the aggressive downscaling. But we have to progress over technology. We have to progress over the need of the day. So some mechanism have been brought in to control this, but we cannot totally eliminate that. That means this hot carrier degradation, oxide breakdown, filtration, all will be present. So we have to limit the current to some extent. That means we have to take care that the current does not go past this particular limit. Also, we have to keep and watch on what is the value of maximum field that the design circuit is subjected to. Okay, so keeping all this into in your what you call purview, we need to take action. That means always we be aware of the physical limitations that will lead to downscaling. So there will be at one point of time we cannot go below these dimensions. We have to stop and look for other mechanism to improve the say on the architecture side. Say we go for parallel processing, pipelining, all these things. Okay, or even the logic design we have to improve instead of going for technology improvement, right? So apart from silicon, germanium technology is there, then carbon nanotube, all these things. But in our digital electronics course, digital VLSI course, we restrict mostly to MOS technology. Okay, so various physical limitations that appear with scaling restrict the amount of feasible scaling for some device dimension. The scaling may be carried out on a certain subset of MOSFET dimensions in many practical cases. That means sometimes we look for a effective combination of constant voltage scaling and constant field scaling. That means relentlessly we do not carry out constant field scaling always or constant voltage scaling, because for practical purpose we need to uh, adopt constant voltage scaling in some cases. But again, constant voltage scaling has its uh, own undesirable features, like these things: power increase, power dissipation increase, then power density increase, and also other second order effects like electromigration, hot carrier degradation, oxide breakdown, electrical overstate, etc. So we have to be aware of this, and we have to be careful in applying constant voltage scaling and constant field scaling into distinct segments. Okay. So till now, any doubt? Yes, please. Okay, is everything clear? Or yeah, Aditi, Meena, Alex, Ambuj, Amit, Ankit, Ankur, Arijit, Arjit, Ayush. Yeah, any doubt? Please let me know.
No doubt.
Father Krishna, Bipin, Surendra, Dinesh, Divank, Bharat Kumar, Fevin. Yeah. So, Gurmeet, is anything? Everything fine? Gurmeet,
Yes,
Himadri.
sir.
Okay, okay. Yeah, Janisaran. Okay.
Excuse me, sir.
Any doubt? Let me. Yes, 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 yes. Yeah, yeah, yeah.
Sir, this
Any
is
question?
regarding the mail I sent to you.
Gurmeet, yes, yes, yeah, yeah, yeah.
Yes, sir.
Yeah, actually, yeah, from the viewpoint of circuit designer, it is better that you need to think of the threshold voltage as a component, as a combination of four components. But this semiconductor device modeling that you studied there, you made some mention like this. For strong inversion, it should be higher than 2.5. Okay, I'll look into that. I have not found time to study about this because we have done some. We have to keep. I am now working like the acting HOD, so a lot of other admin tasks are there I have to perform day by day. So let me see. I'll try to find some time to look into this. But for the time being, let us stick to that means the threshold voltage having four components. One is the uh, work function difference. The second one is your need to make the that change of the surface potential by 2 phi f. Then third one, due to the need for counteract or offset the depletion area charge, and fourth one is your need to balance out the positive sodium ions. Let us stick to this. That means VT is equal to that phi GC minus 2 phi f minus QB CX minus QX by CM. Let us stick to this for calculation of threshold voltage. Okay. And that if I find time, I'll look into that surely. Okay, as you have studied in CVD's book. Okay.
Actually, sir, I have sent you the page number also. So,
Yes, let me find time. Okay.
yeah. Okay,
Sure.
sir.
Okay, dear friends, any more doubt?
Sir,
Yes, yes. Yes,
sir, in
Amit.
the numerical, sir, that you have explained in the starting, sir. Sir, can you open that slide, sir?
Okay, today, no. Yeah. Here, not for the estimate of parameters or even earlier than that.
So for the estimation of that threshold voltage at when
Yes,
when
yes, yes,
goes
yes,
to
yes.
what is
Yeah, yeah, yeah.
voltage zero.
Exactly, exactly. Yeah, yeah. Oh, sorry, sorry. I think it is there.
It was on
Yeah,
page
see.
number four, sir. Mouse slash page number 4.
Mm. So this is regarding uh, getting a experimental
No,
setup
no,
and
sir.
trying to gauge the
One,
value of, yeah,
sir, one more page
right
previous.
now, previous method. Okay, yeah. Oh, sorry, or even prior to that. Yeah, yeah. So what is the question? Yeah, Amit.
Sir, so you calculated that pi f is equal to the for the polysilicon gate, sir, in the numerical.
Uh,
You said that it is highly doped, so we can take 0.55 volt value.
oh yes, that is. You can tacitly assume that as the ND, the donor concentration was much higher, 10 to the power 20, whereas the if you look at the acceptor concentration, that was 10 to the power 16, and also if you consider the intrinsic silicon constant, that is even lower, 10 to the power 10, 1.45 into 10 to the power 10. So if you compare these values, see 10 to the power 20 is orders of magnitude higher than the likely doped p-type substrate. So 10 to the power 20 means excessive doping density, and you can tacitly assume that the conduction band age is almost coincident with that means the Fermi level. The Fermi level moves up and becomes coincident with the EC. That is, we can tacitly assume that the polysilicon gate is degenerate semiconductor.
Sir,
That means
can
it
we
is
not
a n-type degenerate.
sir, can we not
Yeah,
calculate using VT into a ln ND over NI using that formula, sir?
it is not required actually. We can tacitly assume something that means degenerate semiconductor. Yeah, where is it? Yeah, it's not there. Yeah, so in that example, 10 to the power 20 means you need not calculate using that formula. Because there you have to need some other concept like density of states and all that. So that will be deep into the device physics. So let us tacitly assume that EF will be coincident with EC. Okay, that will simplify the calculation of electrostatic Fermi potential. And similarly, suppose you have got, and that was we are considering say N-type polysilicon gate. Suppose you have got P-type polysilicon gate, and we say that the acceptor concentration is 10 to the power 20. Then, for simplicity, we'll assume that the Fermi level is almost coincident with EV. Okay, so for degenerate p-type semiconductor, Fermi level is coincident with the EV. That means the top of the valence band. Whereas for degenerate n-type semiconductor, the bottom of the conduction band will be almost coincident with EF. So EC and EF will be coincident for degenerate n-type semiconductor, whereas for degenerate p-type semiconductor, EV and EF will be taken to be coincident. Okay, I mean, let us
Yes, sir.
assume that because on the circuit designer side, we cannot go deep into the device physics. Okay, I lose track actually. That you have to consider several what do you call statistics like Maxwell-Boltzmann statistics, then Fermi-Dirac statistics. Okay, Gauss-Einstein statistics, all these things. Then the constant of density of states. So that I lose track actually. So let us tacitly assume that for degenerate p-type semiconductor, EV and EF will be coincident, whereas for degenerate n-type semiconductor, EC and EF will be coincident. Okay, so that will
So,
make the calculation easier. Yes.
yes, sir. So there will be some specific values, sir, that we can take that.
Yes,
Suppose
yes,
that
of course. Yeah, it will be mentioned. Don't worry. That we have to make things simpler. Now we'll lay stress on the design aspect. Here we see the essence of the electrical characteristic as well as the physical characteristic. That will be that will cannot what you call leave out. even though we are studying digital VLSI. But later on, that will be will always pay respect to the device aspect, and then we'll take up the design aspect and also how to calculate the salient features, voltages, power distribution, current. That will be our prime motive. Okay. In the beginning of the course, we are studying some device aspect. Later on, we shall move over to that means the scaling we have studied as we are in the deep submicron era. So what are the features of particularly next we'll study about the short channel effect, the narrow channel effect. Okay, then we'll move on to MOSFET capacitance, and then having equipped our knowledge with this concept, then we'll move on to design of inverter, and then combinational gates and all that. As we cannot do it with the basic device physics, so we just have a we are showing we are glancing through the device physics, but mostly our concentration will lie somewhere else. That means in the design aspect. That's I think you have got another class now, no? Dear friends. Hello, you are present? Or okay, probably
Yes,
you'll have
sir.
another class to you have another class to attend, no? Now? At 10
Yes,
o'clock?
sir.
Yes,
Okay.
sir.
Okay, then thank you very much. Again, tomorrow we shall meet at 10 o'clock. Okay. Meanwhile, I'll upload the notes. I think you are getting the notes in the MS folder, na? All of you. Okay, Tausif, you are fine?
Yes, sir.
Yes, sir.
Okay. See you, see you. Okay. Please stay healthy, stay fine. Take care. All the best. Fine. Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank
Thank
you.
you, sir.